In this standard, we're going to learn how to simplify and rewrite expressions involving radicals and rational exponents, or radical expressions. Terms to know. Product property of radicals. The square root of a product is equal to the square root of the factors. Quotient property of radicals. The square root of a quotient is equal to the quotient of the square roots of the numerator and denominator. And then rationalize the denominator. To be in simplest form, the denominator of a fraction should not be irrational. Remember, irrational is any number that cannot be written as a fraction. For example, pi, square root of 2, those are irrational. Therefore, the denominator of a fraction should not contain a radical. To rationalize the denominator, convert the fraction into a form where the denominator has only rational, fractional, or whole number values. Here's an example of the product property of radicals. The square root of a product is equal to the square root of the factors. For example, the square root of a times b is the same as the square root of a times the square root of b. Also, the square root of a times b squared equals square root of a times the square root of b squared. And I can simplify b squared to b to the square root of a. Now that I've done that, let's get into some numbers that'll help it make a little bit more sense. So to simplify a non-perfect square, we have to find a factor that makes up that 45 that is a perfect square. So I break down the square root of 45 into 9 times 5. And the reason I do that is because I can simplify 9, because 9 is a perfect square. So I rewrite it as the square root of 9 times the square root of 5. Now the square root of 9 is 3. I can simplify that. The square root of 5 is a prime number. I cannot simplify that anymore. So I leave it as 3 times the square root of 5. Now let's do 24. Now the factors of 24 are 1, 24, 2, 12, 3, 8, 4, and 6. Okay, so all of those are factors of 24. And I need to find one that has a perfect square. Well, the only perfect square that makes up 24 is 4. So I'm going to rewrite that as the square root of 4 times the square root of 6. I can simplify the square root of 4, and that becomes 2. Square root of 6 cannot be simplified, so my answer is 2 times the square root of 6. The square root of a quotient is equal to the quotient of the square roots of the numerator and the denominator. The denominator cannot be irrational. For example, this guy, the square root of b, if it cannot be simplified, I cannot leave it that way. So, let's do this one right here. The square root of 18 and the square root of 50, and both are being divided by one another. So I would rewrite that as this. The square root of 18 divided by the square root of 50. And I'm going to baby step this. I'm going to do the 18, and then I'm going to come back and do the 50. So I'm going to go ahead and do this. I'm going to break this apart into the square root of 9 times the square root of 2, because 9 is a perfect square, so I'm going to break that apart. Square root of 9 is 3. Square root of 2 cannot do anything else. My numerator is finished. Now let's break apart the 50. The biggest perfect square, that's the main goal. You want to find the biggest perfect square that goes into 50. The biggest perfect square here is 25. So I rewrite that as the square root of 25 times the square root of 2. Square root of 25 can be simplified, and that becomes 5. The square root of 2 is not. Now here's the problem. I cannot leave that square root of 2 in the denominator. I have to rationalize the denominator. To get rid of this, I have to multiply the numerator and the denominator by the square root of 2 because I cannot leave the radicand, an irrational number, in the denominator. So I'm going to do that now. Now I'm going to rewrite 3 square root of 4 divided by 5 the square root of 4. Okay, you see how I'm baby stepping. I'm not doing too much at one time. If I do too much, I'm going to get confused. So I'm going to baby step this. Now, 3 to the square root of 4 becomes 3 times 2 because the square root of 4 is 2. And then 5 to the square root of 4 is going to become 5 times 2. And I get 6/10, and that can also be written as 3 over 5. Okay, if you want to pause the video, here's another example of rationalize the denominator. Now, combining like terms. When combining like terms, you can only combine the ones with the number in the radicand is the same. So for example, 4 to the square root of 10 plus the square root of 13 minus 9 to the square root of 10. So remember when in 6th grade you learned how to do a problem like this, x plus 2x plus y minus 3, and I would tell you to circle my x's, square off my y's, and triangle the constant. This is essentially the same concept, except now you're doing it with a radicand. So my first step would be circle the ones with the square root of 10. And as you can tell, I'm circling the negative with the 9 because it needs to stay together. And I'm going to square off the 13. So in all reality, there's only 2 things I can combine here. And that's 4 to the square root of 10 minus 9 to the square root of 10. Now, as you can tell below here, I've placed these in parentheses. Here's the reason why. That square root of 10 is kind of like when you're adding and subtracting fractions. You do not combine the denominators. Same concept here. When you're adding and subtracting with radicands, those radicands just stay the same. You don't mess with it. So I combine 4 minus 9, I get negative 5 to the square root of 10 plus the square root of 13. As you can tell, I didn't do anything with this. The reason why, it was an unlike term. There was nothing I could combine it with. All right, first example, 7 minus 2 to the square root of 21 plus the square root of 21 minus 6. So I'm going to triangle off my constants. As you can tell, I'm keeping the negative with the 6, and then I'm going to circle my others. I'm now going to rewrite negative 2 to the square root of 21 plus the square root of 21 plus 7 minus 6. Now, you might be thinking to yourself, well, there's no coefficient with the square root of 21. Okay, it's just like the coefficient if it was x. There is a given 1 there. So that's negative 2 plus 1. That becomes negative square root of 21 plus 1. And I'm finished. Now, dealing with the distributive property. This is just like what we did in 6th grade again. You distribute the square root of 5 here and here. Now, you know how I said a second ago, you do not, when adding and subtracting radicands, you do not combine. When multiplying with radicands, remember, you can multiply those 2 together, okay? So 4 times the square root of 5 becomes 4, the square root of 5, minus the square root of 5 times 20. I'm now going to rewrite 4 square root of 5 minus the square root of 100. 4 square root of 5, the square root of 10 is 10. And I'm finished. To solve this problem, you take your first term, the square root of 7, and you multiply it to the square root of 7 and the second term. Then you take the 3, you multiply it to the square root of 7, and then the negative 2, the square root of 3. So let's do that now. Square root of 7 times the square root of 7 is going to be the square root of 49. I will simplify that in a few minutes. So that one's finished. And then negative 2, the square root of 21, because 7 times 3 is 21. Now I distribute with the 3, and I get plus 3, square root of 7, minus 6, the square root of 3. I now simplify all that I can simplify. The only thing I can simplify is the square root of 49, and I get 7 minus 2, the square root of 21, plus 3, the square root of 7, minus 6, square root of 3.